Hello.
Hi.
Welcome to the Wearable Robotics Laboratory in Aerospace. We are based in Cushing, 110. I am Professor Edgar Bolivar, and it's a pleasure to introduce you to the lab. We started in 2021, so most of the things that you see here are new equipment. In the mechatronics area, you will see a workstation where we control our biomechanics. Within our biomechanics computer, we have control of ground reaction forces and markers in the biomechanics space. Here you see an example of somebody who is going to do a sit-to-stand task. And you will see here on the right, ground reaction forces. You see markers that we attach into the participant's body, and by the connection of the markers and the ground reaction forces, we can understand better about the biomechanics of the person, joint movements, muscle action. So that's how we see the effect of our robots on the person. Now, in this area, we actually developed the robots. Right now, we'll introduce you to the open source like version 2, which is one of the robots we designed. Before we do that, let me show you one of the printers that we use. We use this Markforged Mark II. This printer allows us to do composite material printing, 3D printing. So we have carbon fiber, Kevlar, high strength, high temperature fiberglass. So you get parts that are very rigid. You can 3D print them, so you can see the value of being flexible with the manufacturing. So for example, you can get curves. You can print parts overnight. So that allows you to iterate super quickly. In here, there is an example. This part failed in the printing process, so please forgive me for that process, just an attempt. But this is a knee joint for an exoskeleton to help people during the sit-to-stand task. And we are going to include parallel elasticity to reduce the motor size. So in the end, you have an exoskeleton that is light, and it helps you do sit-to-stand tasks. This project is related to people with reduced mobility, mostly older adults, where unfortunately most of the things that they do in terms of exercise is to stand, move to a wheelchair, and then sit. You may be surprised how much research we can do just on that task and how much we could be of help helping that task. We have a regular soldering station, nothing very much to see there. We have also another workstation. Normally, the students may have a dedicated space, or undergraduate students have a floating desk. So you see here, as an undergraduate student, people just come here, they take one of these seats, people can connect to any of these computers, so it's in an on-demand basis. Graduate students have more dedicated spots. And so now, welcome to the biomechanics area. The markers that I showed you at the beginning are tracked by those cameras. That is an OptiTrack system. We have 12 of those cameras. And through the cameras, we can track the position of markers with accuracies of sub-millimeter in this volume. So that's super helpful to all of us. We connect that with ground reaction forces that we have on this treadmill. This is a split belt treadmill, so we know ground reaction forces on each leg. We also have an instrumented walkway. Each of those force plates allows us to measure the ground reaction forces. And the cool thing is that we can move this walkway, put it that way, and so we can have studies where we do walking and sit or going upstairs, because now we have instrumentation on the stairs. So if you're curious about projects that can help people in everyday conditions going outside, here we have a good setup for that kind of research. I'll introduce you to the open source lab project. Within the lab, we focus on optimization problems that could be solved in real time or have global solutions. And the applications could be many. In this case, we have an application in control. We want to control activities that are not defined by periodic tasks. And so we need an optimization problem to solve non-rhythmic motion, in this case, picking up an object. We're going to control this leg for somebody that is going to pick up an object. This is a knee ankle prosthesis. It has the motor for the knee, the motor for the ankle. So our first year graduate student, Mohsen Alisade Nogani, is developing the control strategies to do that task. We see here the workstation for our other PhD student, Kang Yang. is understanding how to use compliance to reduce motor size and motor mass for the power prosthesis. We use computer optimization to actually develop finding the right stiffness that minimizes the motor mass. So just to give you a concluding remark, things that we do in the lab, we do the hardware, the development of the wearable robot. It could be a power prosthesis, it could be an exoskeleton. We do the software, we do the control side, and so through that, we also want to understand the effect that those robots have on the person. So that's how we know if knees, ankles, hips are having less fatigue, having less forces once we use our devices. So we hope to see you here. It's an amazing time to be at Notre Dame in terms of the robotics community. We have multiple faculty. You're all welcome to ask questions. Please take us into account, and we hope to see you here at Notre Dame.